Okay, good morning to everyone, to my classmates, and especially to you, Sir Raymond Endangan. Welcome, and welcome to my final report in Trigonometry. But before anything else, let me handle this floor to introduce myself. I am Gapor Caral Justin B. I am 21 years old. My year in course in this year is Bachelor of Secondary Education, major in Mathematics 2. So my hobbies are outdoor games and indoor games such as volleyball, basketball, Scrabble games, damath, and etc. I like scouting also. But before anything else, let's have a prayer first. Heavenly Father, enable me to teach wisdom, for I help to shape the mind. Equip me to teach with truth, for I help to shape the conscience. Encourage me to teach with vision, for I help to shape the future. Empower me to teach with love, for I help to shape the world. Amen. Okay, so in this final video, or in this final report, we're gonna talk about how we are going to verify trigonometric identities, it is not easy topic, but here's what we need to do. Typically, you'll be given a problem with an equation. What you need to do is to show that the left side of the equation is equivalent to the right side of the equation. So, actually, there are a lot of questions in my mind about how we are going to verify trigonometric identities. What are the importance of verifying trigonometric identities? What are the steps on verifying trigonometric identities? But here is some background or some knowledge about trigonometric identities. So trigonometric identities are used in calculus to simplify trigonometric expression, determine derivatives of trigonometric functions, and change the form of some integrals. So simply to say that trigonometric identities, meaning there are a lot of functions or changes that we are going to form with the use of integrals. Okay, so next. So here are the hints for verifying identities. Hints or our sort of idea on how we're going to verify identities. So first, learn the fundamental identities. So whenever you see either side of a fundamental identity, the other side should come to mind. Also be aware of equivalent forms of the fundamental identities. So just read or just look at on my PPT. For example, sin squared theta is equal to 1 minus cosine squared theta is an alternative form of sin squared theta plus cosine squared theta is equal to 1. Then, number 2, try to rewrite the more complicated sides, because in verifying identities, we must ensure that every detail must be located or every detail must be found on that equation. So we need to try to rewrite the more complicated side of the equation so that it is identical to the simpler side. So meaning identical, both sides are equivalent. Then in number 3, it is sometimes helpful to express all trigonometric functions in the equation in terms of sine and cosine and then simplify the result. So, in number 3, it is more helpful to express all trigonometric functions in the equation in terms of, because in the verifying identities, every detail is mainly observed. Number 4, usually, any factoring or indicated algebraic operations should be performed. So, in verifying trigonometric identities, we're going to use factoring, or we're going to factor out equations, or sometimes we're going to use for method here just to perform the indicated operations. These algebraic identities are often used in verifying trigonometric identities, and as you saw in this PPT, that for example here, x squared plus 2xy plus y squared is equal to x plus y squared. Then x squared minus 2xy plus y squared is equal to x minus y squared. So that is the factor form of x squared minus 2xy plus y squared. Then x cubed minus y cubed is equal to x minus y multiplied by x squared plus xy plus y squared. Then x cubed plus y cubed is equal to x plus y multiplied by x squared minus xy plus y squared. Then x squared minus y squared is equal to x plus y multiplied by x minus y. So as you can see, or as we can observe, that every detail is being factored out. For example, the expression sin squared x plus 2 sin x plus 1 can be factored as sin x plus 1 squared. So the sum or difference of two trigonometric expression can be found in the same way as any other rational expression. For example, let's make it clear first. For example, 1 over sine theta plus 1 over cosine theta is equal to 1 multiplied by cosine theta over sine theta multiplied by cosine theta plus 1 multiplied by sine theta over cosine theta multiplied by sine theta. So what we're going to do is we are going to write with the LCD, or the least common divisor or least common denominator. It's equal to cosine theta plus sine theta is over sine theta multiplied by cosine theta. So therefore, if we're going to relate a to the other side or to the right side, a over c plus b over c is equal to a plus b over c. So that is the result. So that is for number 4. And next, in number 5. Okay, in number 5, when selecting substitution, keep in mind that the side that is not changing because it represents the goal. For example, to verify that the equation tan squared x plus 1 is equal to 1 over cosine squared x is an identity. Think of an identity that relates tan x to cosine x, in this case because secant x is equal to 1 over cosine x and secant squared x is equal to tan squared times x plus 1. The second function is the best link between the two sides. So we must keep in mind that the relation between two is equivalent. Number 6, so last hint for verifying trigonometric identities. If an expression contains 1 plus sine x, multiplying both numerator and denominator by 1 minus sine x would give 1 minus sine squared x, which could be replaced with cosine squared x. Similar procedures apply for 1 minus sine x, 1 plus cosine x, and 1 minus cosine x. So those are the 6 hints for verifying trigonometric identities. Okay, so here are some, list in the board are some techniques that you are used to verify trigonometric identities. First, convert to sine and cosine. A plus b to c and c to e plus b. Then number 4, division, multiplication, multiply by the conjugate. And number 6, factor and FOIL. So these are the 6 some techniques that you are going to use to verify on how to verify trigonometric identities. So here are some identities. So I just want to give you some identities in trigonometry. So, for example, this, what you see in the listed in the board are some identities. So for example, sine squared x plus cosine squared x is equal to 1. Then 1 plus tan squared x is equal to secant squared times x. Then 1 plus cotangent squared of x is equal to sec squared x, or cosecant squared x. And for secant x is equal to 1 over cosecant x. Then cosecant x is equal to 1 over sine x. And for tangent x is equal to sine x over cosine x. And for cotangent x is equal to cosine x over sine x. Then tangent x is equal to 1 over cotangent x. Okay. So now, let's have an example. So it being stated in Lial, 11 edition Lial, the book of Lial, it is being stated in every example. I think we have six example here, or I think 5. Okay. So let's have example 1. So as I'm making this PPT, I want to make a little bit explanation, but as I observe in giving example, it is being clearly discussed this example on how we are going to verify an identity. So what I am going to do now is I am going to express or explain what it is being said. So example 1, verifying an identity, working with one side. So what we're going to do is we're going to work with one side. So first, verify that the following equation is an identity. So our goal here is to verify if it has an identity or not. So the situation given is cotangent theta plus 1 is equal to cosecant theta multiplied by cosine theta plus sine theta. So solution, here is the solution. So it does both give us the solution on how we are going to find or how we are going to verify trigonometric identities. So let's move on. We use the fundamental identities to rewrite one side of the equation so that it is identical to the other side. The right side is more complicated, so we work with it, suggested in Hand 2, and use Hand 3 to change all functions to expressions involving sine or cosine. So we must use the Hand number 2 and the Hand number 3. So let's proceed. So here are the steps. So right side of the given equation, cosine theta. This is the right side of the given equation. Cosine theta multiplied by cosecant theta multiplied by cosine theta plus sine theta is equal to 1 over sine theta multiplied by cosine theta plus sine theta is equal to cosine theta over cosine theta over sine theta plus sine theta over sine theta. So as you can see that in this part in the right side, the equivalent of CEC or the equivalent of cosecant theta is equal to 1 over sine theta. That is why we have a 1 over sine theta there. Then let's move on. Cosecant theta over sine theta plus sine theta over sine theta, we must use the distributive property in which A multiplied by B plus C is equal to AB plus C. So therefore, our answer is cotangent theta plus 1. So left side of the equation. So this is the left side of the equation. So the left side of the equation is the cotangent theta plus 1. Okay. So the right side is cosine theta over sine theta is equal to cosine theta. Then the sine theta over sine theta is equal to 1. That is why cotangent theta plus 1 is equivalent to the left side and to the right side. So the given equation is an identity, or is it clearly to say that it has an identity. The right side of the equation is identical to the left side. So meaning V has an identity. So there is a graph here that will explain that they have an identity. So for theta equals x, so y equals cotangent x plus 1, and once y squared is equal to cosecant x multiplied by cosine theta plus sine cosine x plus sine x rather. Okay, so the graph coincide which supports the conclusion in example 1. So meaning this is just a supporting detail on the example 1 in which it has an identity. Okay. Okay, so now let's move on to the next topic in example 2. In example 2, we are going to verifying an identity working with one side again. So verify that the following equation is an identity. So the given situation is tangent squared multiplied by x. 1 plus cotangent squared x is equal to 1 over 1 minus sine squared x. So here is the solution. We work with a more complicated left side. So we always put in mind that we are going to work first on the complicated side as always suggested in hint 2. Again, we use the fundamental identities. Why we need to work first the complicated side? It is because if we solve for that complicated side, it is easy for us to have the identical equation on the right side. So here is the left side of the given equation. Tangent squared x multiplied by 1 plus cotangent squared x is equal to tan squared x plus tan squared x multiplied by cotangent squared x. So we use here distributive property. Then is equal to tan squared x plus tan squared x multiplied by 1 over tan squared x. So in the right side, cotangent squared x is equal to 1 over tangent x. So, okay, let's make it, let's zoom it bigger. Okay. Now, is equal to tan squared x plus 1. So, tan squared x multiplied by 1 over tan squared x is equal to 1. That is why we have 1 there. So, secant squared x is the Pythagorean identity of the equation. And next is 1 over cosine squared x is equal to secant, or the right identity or the right identical equation is secant squared x is equal to 1 over 1 cosine squared x. So it's equal to 1 over 1 minus tan squared x. So this is the right side of the given equation. So it's the given equation, it is being used about the Pythagorean identity. Now, because the left side of the equation is identical to the right side, the given equation is an identity. Now, as you can see, that every detail has an identity. Now, if we are going to summarize it all, the equation has an identity equation. And here is the supporting detail for that, or the graphing, or the graph that can support that our equation has an identity. So the screen supports the conclusion in example 2. So as you can see, y1 is equal to tan squared x multiplied by 1 plus cotangent 2, or cotangent squared x, cotangent to the power of 2, I mean. Y squared is equal to 1 over 1 minus sine to the power of 2x. So I'm sorry if I have a little mistake. I'm saying to the power of 2. In saying the power 2, I am saying it squared. I'm sorry for that. Okay, that's a little bit error. Let's have another example. So I skip example 3 and example 4 because it talks about the same in example 1 and example 2 about verifying an identity working with one side. So let's have another example in which we are going to work with both sides. And for example, in example 5, verifying identity working with both sides. Verify that the following equation is an identity. So we are going, what is our goal here is to find if it has an identity. So both sides are identical. So the given situation is secant A plus tangent A over secant A minus tangent A is equal to 1 plus 2 sine A plus sine to the power of 2A over cosine to the power of 2A. So here is the solution. Both sides appear equally complex. So we must put in mind that it is appear equally complex. So we verify the identity by changing its side. So in finding the identity also, we're going to change its side into a common third expression. We work first on the left side, multiplying the numerator and denominator by cosine A. So let's move on. So secant A plus tangent A over secant A minus tangent A is equal to secant A plus this secant A plus tangent A over secant A minus tangent A is the left side of the given equation. So it equals to secant A plus tangent A over secant A minus tangent A. So it is being said that we are going to multiply the numerator and denominator by cosine A over cosine A. So therefore, the answer, the next step is secant A cosine, secant A multiplied by cosine A plus tangent A multiplied by cosine A. So what we have done this step is we do the distributive property. Then is equal to 1. So secant A cosine, secant A multiplied by cosine A divided by secant A multiplied by cosine A is equal to 1. So that is why we have a 1 there. So 1 plus tangent A cosine A over 1 minus tangent A cosine A. So secant A or cosine secant A multiplied by cosine A is equal to 1. That is why we have the 1 also there. So 1 plus sine A over cosine A multiplied by cosine A over 1 minus sine A over cosine A multiplied by cosine A. So in the right side, tan A is equal to sine A over cosine A. That is why we multiply it sine A. So what we are going to do now is we are going to simplify. So 1 plus sine A over 1 minus sine A is the simplification of the given situation. Cancel out the cosine and the denominator of the cosine. So that is why we have the 1 plus sine A over 1 minus sine A is the remaining or the simplification. So that is the example on 5 on how we are going to work with both sides. So now let's have the example 6 on verifying, and here's the other, just skip the example 6. Let's continue first. So there is another description or another explanation on finding or verifying the given situation. On the right side, I forget to tell that that we explained a while ago is the left side of the given equation but now we are going to find out on how we are going to factor out the right side of the given equation. So 1 plus 2 sine A plus sine to the power of 2A over cosine to the power of 2A is equal to 1 plus sine A squared or to the power of 2 over cosine to the power of 2A. So what we're going to do is we're going to factor out the numerator, in which x squared plus 2xy plus y squared is equal to x plus y squared, as example, as given in the hand in verifying trigonometric identities. Then next, it is equal to 1 plus sine A to the power of 2 over 1 minus sine to the power of 2A. So cosine to the power of 2A is equal to 1 minus sine A. That is why we have a 1 minus sine to the power of 2 here. Because we we substitute the value of cosine to the power of 2A is equal to 1 plus sine A to the power of 2 over 1 plus sine A multiplied by 1 minus sine A. What we do here is we factor out the denominator, in which it being described as being put in the hand of the numeric finding or verifying trigonometric identities, that x squared minus y squared is equal to x plus y multiplied by x minus y. What we do here is we use the factoring form. So what we are going to do next is we are going to write in the lowest term. So it's equal to 1 plus sine A over 1 minus sine A. So as you observe that the left side and the right side has an identity, or they are equivalent. So we have shown that left side. So let us look at the given data on the PPT. Left side of the given equation and the center is common third expression on the right side of the given equation. So as you can see, they verify that the given equation is an identity. Why? It is because the result of the left side and the right side is equivalent in each other. That is why the equation is an identity. Okay, so here what I said a while ago. That example 6, applying a Pythagorean identity to electronics. So what we are going to do here is we are going to apply it in real life situation or on real objects. So tuners and radios. So as you can see, there is a radio there. Tuners and radios, select a radio station. So when we I think all of us know how to use a radio. So when we turn left or right the tuners and radios, it select a radio station by adjusting the frequency. So a tuner may contain an inductor L and a capacitor C as illustrated in figure 3. So as you can see in figure 3, it has inductor L and a capacitor C. So the energy stored in the inductor at the time t is given by L, or the inductor multiplied by the capacitor, is equal to K sine to the power of 2 pi F multiplied by time. Now, and the energy stored at the capacity is given by C, or the capacitor times the induction, is equal to times time is equal to K. Let's go back. I think I make a mistake. Let's go back in inductor multiplied by time is equal to K sine to the power of 2 pi F multiplied by time. So that's the correct. And the energy stored in the capacitor is given by capacitor multiplied by time is equal to K cosine to the power of 2 pi F to the, multiplied by T. So where F is the frequency in the radio station and K is the constant number, or the total energy A in the circuit is given by E. What we're going to find here is the total circuit energy given. So E is the total circuit, or the total energy in the circuit. E multiplied by time is equal to inductor multiplied by time plus capacitor multiplied by time. So let us show that E, or the total energy, is a constant function. And here is the solution. Total energy multiplied by time is equal to inductor multiplied by time plus capacitor multiplied by time. So this is the given equation. So what we are going to do is we are going to substitute. So it equals to K, or the constant number, sine squared 2 pi F multiplied by time is the substitute of a inductor multiplied by time, and plus the value, or the substitute value of capacitor multiplied by time is K multiplied by cosine to the power of 2 pi multiplied by frequency and multiplied by time. So what we're going to factor it out. So the result is equals to K multiplied by 1, because sine squared theta, or sine to the power of 2 theta plus cosine to the power of 2 theta is equal to 1. Hence, theta is equal to 2 pi ft, or 2 pi frequency times time. So it's equal to K. So therefore, there is what we're going to do. We call this, there is a entity, or what we are going to talk here is the entity or divinity property, because K is a constant and A, or the total energy multiplied by time, is a constant function. That is why we have the entity property.